All right. Hi, everybody. My name is Matt Hunter. I'm the Digital Scholarship Librarian at FSU Libraries, and today we're going to be talking about using 3D printing for data analysis. This is going to be a pretty wide-ranging discussion talking about general 3D modeling workflows, the 3D printing process, and some interesting examples of how one might want to use 3D data in a physical realm for their research or for data analysis. So got a bunch of slides that I'm just going to kind of click through, and then we'll have some time at the end to sort of do a Q&A and questions and things like that. And what I'll do is I'll probably just stop the recording just as we get to the Q&A at the end, just so people will feel free to ask questions. Otherwise, if you have questions, feel free to drop them in the chat and we can answer them at the end. That way they won't be on the recording. All right. So what I want to start with first is that I want to start with a discussion about what it means to create 3D things. And so what normally people think of when they think of 3D printing is one of two workflows, right? So you either start with an idea and you model it, which then generates a 3D model, which is then processed for a 3D printer and then printed. Or you do some form of similar process where you take a physical object and then digitize it somehow, and then you kind of follow the rest of that process of having a 3D model and then running it through the 3D print processing software. And what that often looks like is something similar to this workflow that I've shown. And you either kind of start with an idea, model it, and then run it through the process of slicing and then 3D printing. And we'll get into what slicing means here in a second. But that's sort of one of the two major ways that someone ends up creating 3D models for 3D printing processes. And what I want to, I'm just going to leave this for now and we'll circle back to it near the end. But keep in mind that anything we're talking about today can come from one of these two workflows. So you can either have some form of physical object and then you create a digital object, or you can just have the digital object, which is just a conglomeration of data that has various different referential Cartesian points, right? So you can generate something that has X, Y, Z coordinates as well as, well, mainly just X, Y, Z coordinates, but there are certain things that also have linkages between those Z coordinates and the X and Y coordinates so that you can create things like shapes that end up being interpretable by 3D modeling programs and then 3D printers themselves. So as you're thinking about, okay, if I'm going to create a 3D model of a sculpture, that is going to generate a particular set of computer readable data points. But those data points can be generated by themselves just as you would for any sort of data visualization that would result in like a bar graph or a line chart or something like that. So just be thinking that all we're doing is allowing for 3D to be that third dimension of data that can be represented in some form. Now, whether that's on a 3D printer or just on a computer screen, are it's only removed by these two last sets of steps. So the slicing, which is just rendering an object in a form with instructions that a 3D printer can handle, and then the actual printing process itself. So all of this stuff over here is just data creation for what one would normally do for graphs and charts and things like that. So that linking step is the only part that really becomes physicalized. But when I talk about 3D printing, it's a pretty broad catch-all term, and what 3D printing kind of has come to mean is a conglomeration of 7 different styles of what's often called additive manufacturing. And so starting up in the top left, we have vat photopolymerization. And what this means is that there is a vat of some sort of photosensitive thing. It's normally a type of plasticized resin, which is photosensitive to either UV light or light in general. And what happens is that vat of photopolymer is hardened when exposed to a particular type of light. Sometimes this is done in a way that you sort of have like a really high resolution laser drawing the outline of various different shapes. Sometimes you have it as a sort of layer by layer projection of light. So sort of a large 2D image is projected layer by layer onto this vat of liquid. And then there's normally some form of a Z axis movement here. So you would start with just these three lines, and then you would continue every line until you got to like the next shape that would represent itself as that sliced layer. So, if we're talking about slicing, and I kind of skipped that, but we'll come back to it here in a second. But that slicer basically just interprets what 2D plane is being represented by these three things, and then all the way up through all of this. The Vat photopolymerization does a type of one of two ways of drawing that, either through a laser sort of drawing an outline, which then solidifies that resin, or a larger image projected onto that vat of resin, which does the same thing, just at sort of a larger scale, but it normally takes a little bit longer for that larger projection to work, so they're about the same. The second type is this powder bed fusion, and it's the same idea as the vat photopolymerization, but a lot of times what's happening is that it's not a vat of liquid plasticized resin, it's a container of a sort of powdered or crystallized substrate, which is often fused together by a high-powered light. So similar to the vat photopolymerization, where a laser hardens particular aspects of that resin, here what we often see is something more similar to a just giant bed of metallic particles that are welded together with a laser in that same form of sliced layering system. And so what happens is that in the vat, the resin is cured each layer, and then a small reservoir of resin is resurfaced on the top of that uncured layer to be hit with a laser. Here it's the same idea that a little bit more powder is just laid onto the top of the layer below it, and then that gets welded on, creating these sort of layers that just sort of land on top of each other and fuse together that way. Binder jetting is a similar idea, but what's being injected, I'm sorry, not, it means that something is being injected rather than just fused within a larger vat of either resin or powder. Here you have some form of substrate that reacts to a jet of binders. And so one of the easiest ways of thinking about this, some of the really, really early 3D printing processes was basically just a vat of cornstarch that hot glue or super glue was injected into in very particular ways. So it would just sort of bind all of that cornstarch together with a type of glue. Now, obviously, it's gotten a lot more complex than that, and what you see here is just sort of a representative sample of you can have various different types of binder, and you can have colorants and things like that added as well. So you can print in color here with this binder jetting because the substrate is often just a colorless powder or like a plain white powder. So you can inject dyes as well as glues or binders of some sort to sort of create some really interesting colored objects or various different, if you have different chemical reactions that you can inspire, the binder can act as a catalyst on the substrate to sort of create various different things in that process. So your print head here, which is basically just like the ink, the paper ink printer that you have on your desk, like desktop paper printers, that's the same idea that rather than just injecting layers of ink onto a sheet of paper, you're doing the same thing, but that ink has a little bit of binder in it. So like a glue or cyanoacrylate, as the super glue stuff, cyanoacrylate. Similarly, you have material jetting, and that's using something similar to the binders in this binder jetting process, but it's normally a mixture between the binder jetting and the vat photopolymerization. So you sort of inject some form of substance into a print area that is then cured either by UV light or laser or something like that. So that's sort of like a mixture hybrid process. But oftentimes what you do is, if you can kind of tell, on these three first processes, there's some form of standard receptacle. So here we have like the vat that the photopolymer resides in. Here we have the tray or bucket, really, kind of thing that the powder sits in. Same thing for the powder for the binder jetting. Here, though, you sort of build up a support structure in this material jetting, so that cures at a different rate or is comprised of a different material than the object that you're printing itself. So you sort of have this multi-type jetting that's happening. Now, some of the other processes that are a little bit more complex are stuff like this sheet lamination. And so what you can tell from this one is there's sort of this roll of sheeting material that's drawn across the print bed and then is fused by some form of high energy process. So here, oftentimes what's happening is there's sort of like a roll of plasticized element or metal that rolls across a print bed and then is welded to or laminated to the layer below it. So you're still generating things in layers, just like all of these. And so what you're doing is you're just taking a 2D shape and melding it to the shape below it to create a 3D object. But the sheet lamination allows you to deal with some really interesting, really strong, larger volume type things. So a lot of times there's some really interesting stuff that NASA has been doing with the sheet lamination to kind of create really strong parts that are sheets of really, really thin metal just welded together to create a larger 3D object. I'm going to skip material extrusion for a second and talk about directed energy deposition. And that's similar to the binder jetting and the material jetting, in which not only is there a substance being extruded from the print head or expelled from the print head, but it's also being fused directly onto the thing that it is making. So with the material jetting and the binder jetting, you sort of have this substrate that exists in open air, and then there is some form of binder that is added to it. So in the material jetting, the binder is part of the chemical process that's being injected, and then it is cured using some form of, normally UV sensitive process. Directed energy deposition is kind of a mixture between that, the powder bed fusion, and the sheet lamination, in where material, so like metal powder, is expelled or sort of jetted towards where it needs to be printed, and then a high energy laser or something like that fuses that to the place on which the printing is going to happen. So you can sort of print in a little bit more three-directional ways, so three-axis sort of process. But that's sort of really expensive and really, high tech and not quite as accessible to most people. But the one that most people have normally heard of is this material extrusion. And that's what normal desktop printers are. So you can get one of these on Amazon for like $200. But a material extrusion printer, sometimes called fused filament fabrication or fused deposition modeling, basically takes some form of heat sensitive material. So oftentimes it's some form of plastic filament, feeds it through a heated print head, and then draws a layer of that heated plastic until it cools in the ambient air temperature to create some form of object. Now, what you're seeing here is a representation of a dual extrusion head, which oftentimes allows you to print sort of this vase shape as a normal plastic that we would use in cars or in like water bottles and that kind of stuff, in a 3D substrate of this other one. So these like larger dots here, those are oftentimes when you see this sort of dual extrusion printhead action happening. A lot of times what's happening is that the primary print material is being supported by a dissolvable filament. So a lot of times what happens is that you can print a sort of um, hard, robust plastic in a plastic that dissolves in rubbing alcohol or in water or something like that. And so you can have a little bit stronger of a part because it doesn't need to rest directly on the print bed, or it can have sort of more complex cavities in it that won't sort of collapse in on itself because it's just hot molten plastic resting on nothingness. You can sort of have a little bit more support, and then that support will just dissolve as you go through the rest of the finalization process. But we'll get into that. That's a little bit more advanced technique and stuff like that. But that purple one down at the bottom, material extrusion, that's the standard like consumer accessible 3D printing. At FSU in the libraries, we have vat photopolymerization and material extrusion um, types of printing around campus. There are also the powder bed fusion for sure, and I believe the binder jetting at some of the College of Engineering places. So these are all accessible to you if you have particular needs for them. You just might have to find where they are and sort of get in on a print queue or something like that. The hybrid model I don't want to talk about just yet because it's sort of a proprietary thing that one manufacturer uses to do a mixture of 3D printing and CNC machining. So it's not really 3D printing. It's like kind of a hybrid process, which makes sense because that's what they're marketing it as. But that's where this is coming from. This little infographic is coming from this company. So I don't really want to talk about it all that much because it's not something that you can really do without paying them for it. Okay, so those were like the basic processes of 3D printing and sort of a conceptualized a conceptual overview of the process of making those 2D shapes exist in 3D space. But in order to get to that point, you also need to have some things in mind for when you're creating your 3D objects themselves. And so what I want to talk about now is a couple different 3D design ideas or concepts that you want to keep in mind when you're discussing or thinking about using 3D data and then printing it. So that printing process means that there are some considerations that will need to be kept in mind because when you generate something in a 3D modeling program, it's not necessarily interacting with the rest of the world in the same way that it would as if it were a physical object. So in a 3D modeling program, you don't necessarily have to deal with material strength or gravity or stuff like that. So there's a couple of things that we want to talk about when we're talking about 3D printing for any sort of data analysis. And the first one is that we need to keep in mind this concept of manifold objects. And in the 3D printing world, it's often called water tightness. And that's sort of an idea that says the thing that you've created in 3D space in the computer can exist in 3D space in the real world, so in a physical environment. You also need to keep in mind some things that will come into play during the actual printing process. And this is the stuff like overhangs and supports, infill, and material considerations. And I'm just going to, this slide's been up there, so you hopefully have had a chance to kind of peek over it. But I'll talk about this a little bit more in the next couple of slides. So the first thing that I want to talk about is manifold-ness. So something to keep in mind is that when looking at a 3D object in a computer environment, you are seeing and interpreting things in a bunch of different ways that may not necessarily represent what that object would do in 3D physical space. So here I have a screenshot of two different levels of quality modeling on what looks like a 3D scanned or 3D constructed chair. So one of the hints that it's not been constructed just by a hand modeling, like someone who went into a 3D modeling program and modeled it by themselves, is that you can see that there are some gaps in the 3D model itself. And what this would mean is if we tried to 3D print this, it would cause problems because this space right here, this sort of black void, is a gap in the texture of that model. And while that doesn't really make a difference in this 3D modeling program, because you can sort of see, oh, okay, well, it's still got the shape of a chair, and it looks like a chair because it looks like, a thing that I recognize as a chair. But 3D printers and 3D modeling programs are dumb in the sense that they are literal. So it's not going to interpret that the gap here should be filled in because it's a chair. Um, so what you need to do in order for this to be something that was feasible for 3D printing is go in and sort of fix those gaps. And you can sort of see that the gap here is fixed in this model. So this model over here has been made manifold or watertight. And what that means is that the model itself is it has, you know, both 3D positionality, but then also volume. It has to also have some form of interior and exterior space to it, because as you can see in the example on the right, 3D objects need to have dimensionality. So if you have 3D objects that exist, going back to our beginning geometry, what you're looking at is planes. So like 3D planes. So you have like you have points at the edge of each of these little corners with line segments between them, which all combine to make a 3D plane. But that plane does not have any sort of depth to it or volume to it. So you can't measure a volume of a 2D object that has three-dimensional z-axis positionality. You actually need to have some form of space and volume that the object exists in. So if you were to create this little curve thing in a 3D modeling program and try to print it, there would not be a way for this to happen because the 3D printer cannot interpret this as a 3D shape because it does not have volume. The object on the right does have volume because if you can see, there's sort of this difference between just the single plane and then multiple planes that have connecting, um, volumetric space between them. So that's one of the harder concepts to get your head around when you're thinking of like, well, I drew a thing, it exists, but it has to also be able to exist in 3D space and in physical space. Other things to think about are that when you do 3D printing, the process itself is not instantaneous. It does not just suddenly appear out of thin air. There is a process in which the 3D printer interprets the shape. Okay, so I'm going to back up here for a second. The 3D object that you have in a 3D modeling program in either of these will then have to be interpreted by a slicer. And what that slicer does is it takes that object and it looks at all of the various different 2D planes that make up this object and then interpret those as a set of instructions for the 3D printer to follow in order to draw that layer in 2D space that will then move up in a Z direction from the build plate or the build platform, and then draw the next one. So if you can sort of see what you're seeing on the left, that little 3D printed traffic cone, the slicer knows that if it gets up to this corner of the cone, that edge right there, that first little bit of that edge, is going to be floating in midair. And it can't, the way this print was generated is through the fused, the filament fabrication one. So like a jet of molten plastic is just extruded into thin air. And the way that process works is that it needs something below it to bind to. And so on the ground, you can sort of see that there's like a place where that connected to the build plate, and then the next layer just sort of rested on that molten plastic, and that sort of gave it a space to bind to. But in order for this model to generate that corner, it needed something below it to bind onto. And so there's ways that 3D slicers can create stuff that is called supports. And what that support does is it looks ahead to where an object would otherwise be floating in the middle of thin air and prints from, or extrapolates from there down to the base of the print an idea of how to support that. So it generates these little supports, which are intended to just be sort of broken off or cut away and then discarded so that this model can be printed. But what this example is highlighting is that if you have a model that has some form of verticality, you can get a lot cleaner of a print if you print with an orientation that keeps in mind the physical limitations of your 3D printer. So if you're extruding molten plastic down onto a surface below where the printhead is, it makes sense to sort of have this cone shape, because then you always know that there is something below where the printhead is for that nozzle to print onto. Some other things to think about is that when we do 3D printing, there's some ways to cheat a little bit with that volume that I told you was really important. So normally what we could look at is we could say, imagine this isn't a traffic cone, which we kind of understand are like hollow in the middle. Maybe it's like a pyramid. Um, what one would think of, and since you can't see inside to prove me wrong, let's say that this cone is completely solid with plastic inside of it. And that might have been true in the 3D model that generated this print, but I'm not sure. But what you can do is to sort of save on plastic, to save on time, and to save on a lot of different resources like electricity and stuff like that. You can adjust what the actual infill, and this is the concept called infill in 3D printing, to sort of show what the interior of that 3D model is going to look like. So 100% infill means that that object is legitimately solid. It just fills in every single gap with hot like molten plastic. And 0% infill means that there is going to be an exterior wall on all of the various different faces, but other than that, it is going to be hollow on the inside. But if you go for 100% infill, that's a really heavy, dense object that uses a lot of plastic and takes a lot longer to print, because all of these different lines have to be drawn by the 3D printer, because it doesn't print in sort of like large diameters. It prints just sort of whatever that diameter is of that line. The opposite is true with this 0% infill. If it's completely hollow, it's kind of a weak object. So it only has those thin little plastic walls, which is why you can start having various different percentages of infill depending on what you want that part to do. If you want it to be, still pretty light, but have not be like immediately crushable, you might be able to get away with 5 or 10%, which will give at least some form of interior scaffolding to make that part stronger. If it needs to be something that's going to be put under pressure or something like that, 15, 25, 30, 40, 50, something like that would probably be good, um, without resorting to making it completely solid. So there's always going to be some form of a trade-off with the time and the material cost versus what you want that object to do. So that's just something to keep in mind, and that can be adjusted within the 3D print slicer software that interprets the instructions for the printer to follow itself. Other things to think about, and I was kind of talking about this with that cone example, but overhangs are objects in the 3D print environment in which there is nothing for that object to rest on when the printer goes over it. So you can sort of see there is a short overhang here, this little upside down L. There's not a lot of space for that printer to sort of just spit hot plastic out onto and just have it droop down. Here, though, you sort of see what happens when you have longer and longer overhangs. And this one on the far right shows a really good example of what this printer was doing is trying to print just a straight arm out from around here, if you can see my mouse, around the corner, the armpit of that little overhang. But since this is just hot molten plastic, it's just going to droop in thin air until the printer has something to connect it to. So that's why you start seeing that it just sort of like dangles and droops pretty grossly, because there's nothing for it on the underside to sort of connect to. So that's why you want to try and keep in mind the orientation that you're printing something. But also, that's why you have those things like supports that we saw from the traffic cone example, something to at least give the bottom of the print like a support. Yeah, the support is a plane for that printer to sort of touch onto to create a nice solid bond. Okay, so thinking about materials, we already talked a little bit about how there are various different types of materials that work well with the various different printing processes. So the like uh, powder bed printing example, you can have something as strong as like powdered titanium that's just welded into a super super strong shape, and there are some places in the world that have the opportunity to do that because they have the material budget to do so. But what most common printers, and this is talking about the fused deposition modeling, the fused filament fabrication, the ones that are sort of hot plastic drawn in 2D layers, what you're most likely going to see are these the top three. And so what you have is you sort of have ABS plastic, which is the stuff that you're going to find in any sort of high wear item. So that's the plastic that's most likely going to be in, um, a car interior or in the engine bay of a car. That's also going to be a lot of times what like um, press form plastic is. So anything that's like a exterior panel for like a microwave or something like that. Those are going to be high wear, good wearing, strong plastic types. But it's difficult to 3D print because not only is there a high thermal load that has to be overcome in order to melt that plastic, so the glass transition temperature on that plastic is really high, it's also potentially really dangerous because the fumes of ABS are really dangerous. They're potentially carcinogenic, so if you hang around printers that print ABS, there is a high likelihood that you have been exposed to cancer-causing materials, which is not great. The fumes are also extremely like pungent, so it smells really bad too. So a lot of times in early 3D printing, ABS printers would be in vented locations. So the fumes would be sucked out and like passed through a filter before anyone would have to smell them. Um, and so since ABS is sort of bad for people and had a pretty difficult like thermal properties to print with, the next one on the list was developed. This is polylactic acid, and it's a cornstarch derived plastic made from sugars from um, uh, corn and other naturally occurring biosugars. And so it's sort of a semi-renewable, more eco-friendly plastic that can decompose within sort of a lifetime rather than whatever ABS is, which is hundreds of years at this point. Uh, but what's one of the real nice things about polylactic acid or PLA is that it has a really low glass temperature transition point, or sorry, glass transition temperature point. So you can print things at sort of 150 degrees Celsius rather than ABS, which is like 280 degrees Celsius, which is just a lot of electricity just to kind of heat a 3D printer nozzle for. So the widespread development of PLA sort of really helped kickstart the desktop 3D printing revolution. So that's really nice. The print substance is also really, it's softer, but it's not as, it's not like completely weak, but it's not as strong as ABS. So it's sort of like a decent trade-off. But the third one down, PETG or polyethylene tetrafluoride, plus glycol, because it's suspended in glycol a lot of times in a plasticized glycol environment. But that is sort of the mixture of the two. So it's not, it has a slightly higher temperature, um, working temperature than PLA, but not quite as high as ABS. It also has way better UV resistance than PLA, not quite as good as ABS, but it basically has all the benefits of ABS without many of the detriments. So it's still really strong. It still resists UV radiation really well, so it doesn't degrade as fast. Um, but it's not harmful to breathe in the fumes while it's printing. It's a little bit better for the environment as well. And one of the big things that PETG really, really sort of, you know, succeeded at is that it is higher temperature sensitive once printed, so it doesn't deform as much as PLA, which is really popular because PETG took on a life of its own at the beginning of the COVID-19 pandemic, because that's what people discovered was the plastic that was good enough to 3D print the masks and the sort of face shields with. They could stand up to the hospital sanitization program. So PETG sort of had its day in the sun at the beginning of the pandemic last year. These two on the bottom are more for the Vat photopolymerization or the photopolymer powder processes, and those are the ones that you sort of have a bucket or a vat of one of these plasticized things, and then you sort of inject either light or laser light on it to sort of draw and fuse those bits of particles together. They're a little bit more rare, but a lot of times they're the printers that use those materials have a lot higher of a resolution. And they're also normally a lot stronger, so the bonds between layers are a lot stronger. There have been some PLA prints that I've done that you can just sort of break apart layer by hand. The resin prints that I've done, there's no way that I could do that without like a jackhammer or like a sledgehammer or something crazy. So they're a lot stronger, but they are a little bit more expensive and they're a little bit more dangerous because there are some, potential health risks if handled improperly. So something to keep in mind. All right. For the rest of the presentation, I'm going to show you a couple examples, a lot of examples actually. But what I want you to be thinking about is I'm showing you examples for sort of a couple different areas for use of 3D printing. And the first one I'm going to be showing is using 3D printing for education. So one thing that has become really popular is that 3D printers centrally located in places like libraries or schools have allowed people to interact with things that would otherwise not be easy to get a hold of. And so, what some of the things that I'm thinking of are like here on the left, you see that there's well on this screen you sort of see government provided and government funded sharing of 3D models for educational and learning purposes. On the left, the National Institutes of Health have started working on 3D object sharing repositories that have things like chemical structures and also sort of biology inspired medical imaging derived 3D structures. So what you can do is you can sort of download these models and 3D print them if you want a so the one on the left is the chemical structure for caffeine. If you wanted to download that and sort of have a 3D model of the caffeine chemical, you can do that, and it's generated from data sets derived and deposited into the NIH 3D print repository. The one on the right is it's coronary arteries, so the arteries around the heart with the heart muscles themselves removed, so you can sort of see where those exist in 3D space without being able to or without having to look at like the entire model of a heart. And so you can sort of look at the complex structures of those without needing to find a educational model of a heart that might only exist in like a specialized education store or something like that. So you can just download those and 3D print them if you have a 3D printer. And being able to print the both of those just yourself saves a lot of money and allows you to sort of get exposed to a lot of different things. The one on the right is actually a reconstructed debris field of a supernova that NASA was able to reconstruct from various different data over the last, I want to say, 2 decades. Well, I think it was generated in 2007 or so. So 2 decades prior from that. So since the 80s. But it's from data gathered from the Hubble telescope and a lot of the sort of X-ray spectrograph images of space that you can sort of reconstruct where the debris field of the supernova was, and you can download the reconstructed shape of this supernova and print it if you wanted to. So you can sort of have this 3D um, shape that you can sort of hold and rotate in your own hands to sort of see where this is, rather than just looking at a handful of 2D pictures of, in a textbook or something like that to sort of look at um, that example. Similarly, you can adjust 3D models based on what you want to see. So this is a hyper simplification of the cylinder of an internal combustion engine. And what you can do with a 3D printer is you can print all of the requisite parts to make something like this, and then see how it's constructed so that you can see sort of the inner workings. But then you can also modify the 3D print, the 3D object model to sort of like make cutaways a little bit easier. So if you're into engineering and you want to see the internal processes of like something as complicated as a combustion engine, you can do that with 3D printed models and sort of see the intricacies while this is in motion, and you can sort of just like spin the crankshaft down there at the bottom to sort of watch the process happen without needing to like mill out all of this out of metal, or go find a junkyard car and take a sawzall and cut their engine in half. You can do this with just one cylinder and sort of see how it works. Also, you can try and do other things that aren't necessarily like observational. You can sort of have experiential learning things as well. So there's a big early music education uh, push in 3D printing as well. So you can have things like custom built um, and like really quickly generated musical instruments. So here on the right, you sort of see panpipes, and on the left is a little ocarina. But you can have things like that that can be customized for various different like hand shapes and stuff like that for disability, and uh, just other learning experiences. If you wanted to like play around with the interior cavity of the ocarina or the length of those pipes, you can sort of get the sense of how the acoustics of those things change. So you can sort of adjust that on the fly and then 3D print a new object within a couple hours or so to sort of experiment with all that. Similarly, you can go real crazy and you can start experimenting with some really great mechanical things that you would need otherwise access to like a machine shop to work on. So this is a triaxial tourbillon clock. And what it does is it sort of shows the position of the Earth and the Moon, sort of on that central, slightly northeast southwest axis. Those both rotate in opposition to each other, so you can see the position of the day on the Earth. So whatever faces up is noon, I believe. Whatever faces up on the moon, I believe, is the representation. I think like up at the top there's a little key that you can't really see, but um, the phase of the moon, sorry, the phase of the moon that currently exists, and I think those both rotate to sort of show their position in terms of the month. And then there's an hour, obviously like a minute hour clock on the left. And all of this is 3D printed other than the screws that are holding it to that piece of wood. And so like you can see a couple different small set screws and pins and things like that in it. But otherwise, this is all completely 3D printed, and it all works, which is crazy. So you can look at various different like gearing ratios and things like that and make customized different sizes if you wanted to learn how all of this works. But otherwise, if you wanted to make something as intricate as this, you'd need a lot of time and some pretty high like learning curve um, machining equipment like mills and lathes and things like that. So pretty cool that you can make this on the same technology that you made a tiny little panpipe and a caffeine molecule. So that's all stuff that's sort of like ready generated and for larger aspects. But what if you need some custom tools? So say you're working in a biology lab and you have a pipe holder for various different um, chemical glassware or something like that that you needed, and you needed a specific orientation of those things. Well, you could print a rack for that that you design yourself. And this is, you know, one of the cool things is that it's just being generated from data. So one of the really interesting things is that the International Space Station has a 3D printer on it, and the wrench on the left was one of the first wrenches, or one of the first tools to ever be printed in space. And so the tool brand Cobalt got their name. What a great marketing opportunity for them. But the one on the right is actually a little bit more interesting to me. It is the first object that was designed on Earth for particular uh, needs and use cases in space, emailed to space, and then 3D printed in space. So that is a 3 inch-pounds torque wrench, all made of plastic, that was used to do some tightening on the International Space Station. And that was designed by a contractor at the Jet Propulsion Laboratory, I believe, and then emailed to the International Space Station and printed that way. So, like, talk about a custom tool that was used for like a handful of bolts on the International Space Station that needed to be torqued to exact specifications. So, the ISS didn't come hurtling down in a terrible disaster. Um, but you can also make some other really cool things. You can make housings for custom spectrographs and spectroscopes. Like I was saying, you can do some really cool stuff with like custom mounting hardware or storage things. There are also people that end up 3D printing apertures for some really interesting stuff. There's one that's a mirror-based refraction telescope that was made with I believe it's like PVC pipe and 3D prints. So the mirror itself obviously isn't 3D printed, but like the rest of the structure and the armatures, I believe, were. Whereas those long gray pipes, I think, are just like PVC pipes, and there's a couple bolts and screws in there as well. So that's pretty cool. That I think it's also Raspberry Pi controlled, if I can remember correctly. So you can sort of orient it to particular um, coordinates that way. But that's just a really interesting way of thinking about custom jigs and I'm sorry, not custom apertures and armatures. These are custom jigs. So if you have very particular repetitive tasks that need to be done, either through sort of automation or something like that, 3D printing allows you to create custom holders for those. And so jigs are just a way for a mechanized um, construction or manufacturing process to sort of hold parts that are non-standard or non-flat. And so the one on the left is from, I believe, Dyson. They need to drill and tap a couple different very particular sets of holes in this thing, but since the part itself is sort of like wobbly, they couldn't do it with it just resting on that plate. So they 3D printed a jig and then mounted that in the assembly hardware, and they now use that 3D printed jig to hold that part. On the right, a user on the site Sketchfab needed to be able to press some, I believe it's like 12 gauge sheet metal for replacement parts for part of his car or something like that, and was able to 3D print the form for that, fill it with some resin, and then just press those plates. So that's pretty interesting. Uh, just so that I'm sorry, it's written right on there, 18 gauge stainless steel. So that's really cool that he was able to just sort of design that form himself for replacement parts or whatever. Um, so that's been a lot of stuff that's sort of really interesting for education and then customized tooling. One of the things that 3D printing is really making a wave in is increasing access to stuff. And I'm being intentionally vague about this because what you're seeing on some of these is just like, I don't know. I think it's one of the cooler things that you can do with 3D printing. But what's nuts about this one, and I'm going to give you an example before I explain it too much. This is not a Van Gogh painting. it is a 3D printed replica of a Van Gogh painting. And what happened is that the Van Gogh Museum in Amsterdam took a 3D scan of the sunflowers painting that Van Gogh did and mapped the height of all of the brushstrokes and the particular colors on each of them. So when you recreate a painting like this, a lot of times it's just printed straight onto canvas or printed on some form of like paper backing or something like that. But that doesn't capture the height and the textuality or the 3D-ness of the painting because you don't get the depth of the brushstrokes. And rather than going through and having a master artist sort of recreate those brushstrokes in the same way, um, Fujifilm, I believe, partnered with the Van Gogh Museum and then created this scan that has not only the height relief of the painting itself, but then also they painted that layer by layer with a 3D printer, and then went back through and printed on top of that relief, similar to how you would with like a desktop ink printer, the correct colors. So now there are just really high quality, um, more texturally accurate replicas of, well, I don't know about replica, but reinterpretations, copies of some really famous paintings. So that's really cool. And that's something that couldn't be done without understanding how the sort of layer height aspect of 3D printing worked. Similarly, and I forgot to take a picture of this. My apologies. That was one of the last things I meant to do for this. But one of the other really interesting things is that you can create 3D scans or 3D models of stuff that is otherwise pretty much inaccessible or difficult to access. So this is a really famous Hellenistic Greek bronze statue called the Boxer at Rest, or the Quirinal Boxer. And it was produced sort of around the 4th century BCE. And it's currently held, it was discovered in Rome, but it's currently held at the Palazzo Massimo in Rome, which has been closed for the last year or so. But what you can do is you can go to this scan the world page and look at not only the 3D object, but the picture that I was supposed to post here. I've printed a copy of this that I have sitting on my desk at the libraries. So it's really nice to be able to sort of have a copy of this and sort of look at it from all different directions that you wouldn't be able to since the museum is closed. But, once we're all vaccinated and the pandemic is a little bit more under control, we can go back to Rome if we have the opportunity and the uh, benefit of being able to travel. There's other things that you can't get back. So what we're looking at here is the Temple of Baal Shamin, and the image in the top left is from about 2010. The photo with the explosion is 2015 when the Islamic State blew up that temple, which is from, I want to say, the 300s or 400s BCE as well. And terrible loss of shared cultural shared cultural heritage of the entire world. But what's amazing is that people have been generating 3D models of that temple to try and recreate it. So just the fact that you can try to recreate the temple, um, and even in just sort of like small 3D printed form, is amazing because it no longer exists. So unlike the Boxer, which you can go see in maybe a year or two, that temple does not exist anymore. It's been blown up. So it's nice to be able to try and recapture some of that, at least a little bit, so that it's not completely lost. But increasing access also works in other ways, right? So there's a Italian maker group called Monza Makers that went into a museum and took a height map image of Caravaggio's Flagellation of Christ and reproduced that in 3D printed high relief for visually impaired people. I'm sorry, people with visual impairments that go to this museum, so that they can not only read the Braille image placards, which you can kind of see here and here. They can also sort of run their fingers over the relief of that image itself and sort of get a sense of what it feels like to sort of see that and the sort of height relief and things like that. So that's really interesting that they're able to increase access to that painting, which is sort of visual only, to people with visual impairments. But now we're going to talk about the thing that sort of everybody probably came here for, and which I saved for the last 5 minutes of this presentation: data visualization, data physicalization, tactile and haptic data. And what this is sort of the extension of all of the things we've been talking about already. And what I'm trying to think of is this concept, right? So I don't know if everybody else use these, but I use these in sort of elementary school math classes to sort of get the sense between ones, tens, hundreds, and thousands. And this is all we're thinking about. This is the tactile experience of something that is data related, right? So this is tactile numeracy. But this is a lot older than you might think. So I don't know if anybody is aware or knows about this, but on the top left, what we're seeing is a detail of an Attic red figure vase from, I want to say, I forgot to write the date down, but I want to say, oh no, I did write it down, 490 BCE. So 500 years before the modern era, the Common Era. Athenians voted by dropping black or white pebbles into a bowl to show their vote was either yes or no. So when you tipped out that vase, you could sort of see the quick counting of data in a visual format between either black or white. And you could pile those up and sort of see which pile was bigger. On the right, you have Micronesian maps. So the Marshall Islands, currently in the middle of what is currently the Marshall Islands in the middle of the Pacific, native peoples made maps and charts to show the direction of uh, sea lanes and currents and islands based on this tactile visual representation of sticks, shells, and curved wood. And on the bottom, we have quipu, which are Incan data forms that each line means something. And on those lines, there are various different knots and things tied into the lines that people, researchers still aren't exactly sure what the various different lengths or colors or knots mean, but it's a way to sort of tactilize and make data physical. Here, what we're seeing is a little bit more recent version of this, which is 3D space representing molecules. And so this is Dorothy Hodgkin's 3D model of penicillin, which was viewed from 3 different axes of X-ray chromatography. So where those dots are sort of the intersections of the various different 3 axis views of that molecule. Similarly, we have another way of sort of visualizing data, and this is where I'm starting to get into the sort of more abstract, where if you have an XY plot, you can also add a Z dimension, which gives you another layer of data that you can represent, but you can also add contextual information to that Z dimension, and so that you can have different things such as like color or frequency or something like that. So you can start to get into some really, really complex visual representations of data. And so I'm just going to speed through a couple of these because we're at time, but I want to make sure people have time for questions. But some of these you can sort of see amplitude based on 4-point interference of oscillation and sound waves and things like that. So that's really interesting. You can represent things visually just from height map, which is kind of interesting, and just sort of highlight various different aspects of a 2D plane just to make it a little bit more visually impressive. You can also represent things like archaeological dig sites by recreating the sites in a sort of more hand portable version. So that's what's going on here. It's just a recreation of that excavated site, but 3D printed and then sort of hand painted so that you can carry that around with you to a conference and show it off to people and things like that. You can also model frequency of occurrences for various different things. So this is just a small little data sculpture showing which letters on a keyboard occur the most often and are used the most often. And that's just a really simple way of rethinking what would otherwise be like a bar graph or something like that. It's now become 3D and become tactile. Similarly, you can look at the sort of graphing of 3D occurrences in physical space. So this is a NASA-generated model of the collision of solar winds for Enceladus, I believe. I'm sorry, no, Carinae, Eta Carinae. So that is it exists as a 3D model that is visible through like 3D model viewing software, but once it's printed, you can sort of pick it up and hold it and sort of rotate it and view it from a bunch of different angles, which is just a new way of interacting with that data. Similarly, if you're working with network graphs and things like that, a lot of times those are produced in a way that you sort of have to look at it on a 2D computer screen, and you sort of like move around the nodes to sort of see how they kind of jiggle away from each other. But you can also 3D print those nodes and sort of see the complex interconnections of something like a network. And so these are 3D printed social networks from people who have either mutual friends or send letters or calls to each other or something like that. And these can be generated pretty quickly just through something, as simple as R, the programming language R. So you can generate these, which would normally just be 2D information, but there's an inherent Z dimension to that, so a third dimension in there that can be exported into a 3D um, viewing experience that allows you to 3D print them. So that's always really interesting. And then similarly for this one, this is an apolipoprotein that has some form of three-dimensionality to it, and this is printed in a sort of acrylic resin just to kind of protect it since it's so delicate. But otherwise, this model is just a 3D representation of something that is already a complex organic molecule that would be really difficult to see in its totality if you were to just look at it on a 2D screen. Okay, so that's all I have. I'm going to stop my share and I'll stop the recording as well.